Let's start off by just a summary of what your work is for which you received the Turing Award.
In the world of combinatorial computing, there are many problems that seem to be very difficult. Scheduling classes at a school or jobs at a factory, finding paths in networks to get from one point to another, various problems that arise in commerce, in industry, in number theory, in engineering and so forth, which seem to require for their solution a long, exhaustive search through a set of possible computational choices. A classic example is the so-called traveling salesman problem, in which a salesman has to find a tour through a set of cities which will take him to each city exactly once and return him to his starting point. He knows in this idealized problem, he knows the travel costs to go from any one city to another, and he has to search them through a vast number of permutations of the cities to determine the one for which the total travel cost would be least. So this is an example of a combinatorial search problem where an exhaustive solution would require a vast amount of time. The number of steps would be 2 to the power n, where n is the number of cities, and that exponential growth is enormous. So the question arises in scheduling classes at a school, or jobs in a factory, or dispatching taxi cabs, or a host of other applications, whether there are ways to avoid that combinatorial enumeration of solutions and cut to the chase, so to speak, to get to the correct solution. And there are a number of problems where you can avoid the combinatorial search. For example, if you have a road network and you want to find the shortest path from point A to point B, that can be done very rapidly. Or if you want to sort a list of numbers into increasing order, the number of orderings is exponential, factorial in fact. But it's pretty easy to see that there's a quick way of figuring out the ordering. So the problem arises of defining the boundary between the problems that require exponential search and those for which a quick solution is possible. One way to formulate this problem leads to something called the P versus NP problem. Which asks the question, are there problems for which solutions are easy to verify but hard to find? So for example, if I give you an abstract graph, which is a set of vertices, certain pairs of which are connected by edges, define a clique in that graph as a set of 5 vertices such that all pairwise direct connections exist. So a so-called complete graph with 5 vertices. If a solution is easy to verify, if you have the graph and you're told that vertices 3, 7, 12, 20, and 46 form a clique, you can very quickly consult all the pairs of those vertices and see if all those edges are present. But to actually find a clique of size 5 involves a lot of work. So that illustrates the distinction between verifying a given solution and actually searching and finding a solution. Or similarly, in the traveling salesman problem, if you wanted to know whether the salesman has a tour of the cities that covers less than 10,000 miles, it would be very hard to do, but if somebody gave you a tour, you would just have to add up the costs of the edges and see whether it came to less than 10,000. So we define NP as the class of problems where solutions are easy to verify, and P as the class of problems for which solutions are easy to find. And we believe that there are many problems in NP that do not lie in P. These are the combinatorial search problems that don't seem to be easy to solve. But it remains an open possibility that P is equal to NP. It has not been ruled out. So it's conceivable that there's some magical method that nobody has uncovered that would allow all of these problems to be easily solved.
And how did you get interested in this problem?
Well, I had encountered combinatorial explosions throughout my career. I worked on the traveling salesman problem. I worked on digital circuit design, where in the vast sea of possible ways of interconnecting logical gates, is there one which satisfies a particular constraint? Scheduling problems. I had worked at the boundary between computer science and operations research, and so I was very familiar with many of these logistical problems, and so combinatorial explosions were familiar to me. The immediate impetus was some work by Stephen Cook, who's a fellow Turing Award winner, in which he showed that a certain problem is as hard as any problem in NP. Just to repeat, NP is the class of problems that are easy to verify. So he showed that the satisfiability problem of propositional logic is complete in the class NP, which means that for any problem in the class, there's an algorithm that transforms every instance of that problem to an instance of this satisfiability problem. Satisfiability problem is a fundamental problem in propositional logic. You're given, it deals with Boolean variables, variables that can be either true or false. And in the satisfiability problem, you're given a collection of the statements of the following form. Either A is true, or B is false, or C is true. That's called a clause. It's a disjunction of two or more variables. And you're given a list of each of those as a constraint. You have to choose truth values for all of the variables, such as A, B, C, D, etc. And you have to satisfy all the clauses. There has to be a setting of the variables which makes every one of the clauses true. And the satisfiability problem is to decide, given a collection of such constraints in the form of clauses, whether there is indeed a truth assignment to the variables that makes all the clauses true. And what Cook showed was that any problem in NP, any problem in this class of easy to verify problems can be mapped to the satisfiability problem. It would mean then that if the satisfiability problem were efficiently solvable, all these combinatorial problems would also be efficiently solvable, meaning polynomial time. So it seems very implausible, but still logically an open possibility. When I saw Cook's work, I realized from my experience with combinatorial explosions that many problems beside the satisfiability problem had this same characteristic, that they were universal or complete, as we call it. That all of these down-to-earth problems of scheduling, packing, etc., many of them could also had this completeness property. Intuitively, I knew that this was going to be the case, but to prove it, I had to give reductions, transformations, which took the satisfiability problem into each of these problems to show that if you could solve classroom scheduling, for example, then you could solve satisfiability. And by chains of reductions of this kind, I was able to show that there was a whole equivalence class of problems, all of which were complete, and therefore, in some sense, the hardest problems in NP and the ones least likely to lie in the class P. And it turns out that by now people have added to the thousands of problems to the list using this technique that I introduced of reductions. I now think we call these problems NP complete. And I think of NP completeness as a curse, because once you know that a problem is NP complete, you're virtually certain that you're not going to find a fast, complete algorithm for solving it. And so the search for combinatorial algorithms has to go in other directions, looking for approximate solutions or heuristic solutions or solutions that work on the average. But you know you're not going to solve these problems within polynomial time.
So before you, humanity was cursed but didn't know it.
Yeah. That's right.
I'd like to move a little bit away from the details of your work and more into how you got there. Since HLF is so much about mentorship and the experienced talking with the less experienced, was there anyone in your career, thinking back, let's say, to when you were at the age of these young researchers, who especially influenced you personally?
Well, first of all, my father influenced me because with his teaching style, he was a public school teacher of mathematics. He didn't know a lot of math, but he could draw perfect circles on the blackboard, and he had a easy, entertaining style in the classroom. And occasionally I was permitted to go to his 8th or 9th grade classes and sit in the room. And, since I wanted very much to admire my father, this was an arena in which he looked his best, and so I enjoyed that contact. There was a high school math teacher who gave me a lot of encouragement. In my senior year at Harvard, I was a math major, and I had done reasonably well in the sort of easy math courses through, until I reached the level of starting to take graduate math courses. And I quickly saw that sitting in my course in complex variables, for example, there were people who were just better than I was, younger and smarter. What I didn't know was that one of them was going to win a Nobel Prize, and another one was going to win the Fields Medal in mathematics.
Who were they? If I may?
David Mumford was the Fields medalist, and Ken Wilson won the Nobel Prize in physics. They were both sitting in these classes. And there was another guy who was a freshman who never gained much fame, but was better than either of those guys. So, Harvard tended to get these prodigies. And so my confidence was shaken On the other hand, in the somewhat easier math courses, on probability and statistics, for example, I thrived. And my teacher in one of those courses was a man named Hartley Rogers, who eventually wrote a book on computability theory that's very important. And he encouraged me, he made me feel good about myself, because in those courses I was doing quite well, and I had to position myself somewhere, you know, continuing to have my self-respect because I was good at some of this stuff, but knowing also that in the outer reaches of theoretical mathematics there were people who could dance rings around me, and his encouragement was very important to me.
It's interesting that the positive reinforcement that you're succeeding, which I suppose many of the young researchers have by coming here, you know, by being selected to come here.
Yeah.
What sort of interaction have you had with the students here, with the young researchers, I should say?
Well, I'm very impressed with the way the group was selected. They're from all over. It's fascinating. They're from various African countries where I didn't really know there was even a mathematics or computer science establishment, and they come from all of the continents except Antarctica. Yeah,
they already have their PhDs.
Right. Yeah, and it's just a fascinating mix of humanity, and they're very earnest, and some of them are fairly advanced in their research, and I guess my reaction is has elements of both inspiration and satisfaction and my interaction with them, and impotence, because in some cases it's hard to make contact because they're more deeply steeped in what they're doing than I am, or just because there's a language gap, or because maybe in a few cases, maybe I don't have such a high opinion of what they're doing, and I have to mask that. And there's a frustration in not necessarily being able to help them. I mean, I can help them by listening sympathetically. But sometimes it's very hard work to understand what they're getting at. Sometimes I understand what they're doing, but they know more about it than I do, and there's not much I can do for them. But I try to be optimistic and encouraging, and it makes me realize that the world is a big place, and that there are places other than Berkeley and Stanford and MIT and Harvard and so on where good stuff is going on, so that feels good.
Now, you are a professor at Berkeley as well.
I am a professor at Berkeley, yeah.
You still are, yes.
I'm now, as of last January, I'm emeritus.
Oh, okay.
Yeah.
Would you say that you have a particular style that you use with your graduate students, let's say when they hit a wall?
Everyone is a special case. There have been a few. I've had over 40 PhD students. A couple of them I remember just knew where they were going. They didn't need any help, and in a few cases, they went on to really to greatness. You know. Except for with those exceptions, the great majority hit a wall at some point where, you know, they believe that they can't do it. They go through some loss of confidence or frustration. One thing I can do is to tell them that I get frustrated too. I remember confessing to one of my students that when I go to conferences and listen to all the papers, I somehow get depressed. And she was having the same experience, and somehow hearing that it was happening to me was helpful to her. Some of them really want to work on their own. For others enjoy working in groups. I have to kind of diagnose what works. Occasionally there are some who look as if they're having a lot of trouble doing things on their own, but they do well in collaboration. They like to collaborate, and so each one is just a special case. There's one thing that I don't do is assign the thesis problem. I want them, we can discuss an area, we can discuss some literature, but in the end I want them to choose the problem. And happily, I haven't had to, well, yes, there was one case, a fellow who had set unreasonably high standards for himself. He was very talented and chose an extremely hard problem, and he worked at it single-mindedly for a long time, and finally dropped out and took a job in industry. And it was a case where he was uncompromising in defining the level that he wanted to reach, and when he couldn't do it, he moved on. But for the great majority of them, they've managed to come through and eventually earn their degrees and have pretty good positions.
Now that example raises a question in my mind. How much, when someone hits a wall, how often or how much do you think it's because of the content of what they're studying, and how much do you think it's personal?
The wall is real, but the reaction to it is personal. Yeah, and some people have sunny dispositions and shrug off their frustrations. Others go into a funk. It's a matter of the personality type.
You mentioned those who work well in collaboration and those who work solo, and I hear that dichotomy a lot from mathematicians. Which group would you say you're in?
Most of my best papers are with people who are smarter than I am, so I do like to collaborate. The piece of work for which I may be remembered is the one on NP completeness that I described to you, and that I did entirely by myself. I don't think I'm particularly deep problem solver. I think I'm pretty good at recognizing questions or making up questions, and have a certain degree of facility and knowledge with the tools of mathematics. But I'm not the kind of guy who's going to settle the Riemann hypothesis or some long-standing open question in mathematics.
Although you're well known for having set some your 21 questions, was it the 21 problems?
Right. Right. Yes, I was able to set those problems, but not to solve them.
I just want to take a quick look here. Actually, this is a big question. It's sort of strange to ask computer scientists because, of course, so much has changed in 50 years. There's no comparison. But either in terms of content or environment, how much do you think has changed between when you were the age of these young researchers and now, as far as academic study and success, such as you've had?
Well, when I entered the field of computer science, even before it had a name in 1955, when I decided to do my graduate work at the Harvard Computation Lab, there were all kinds of natural problems sort of lying there on the ground, accessible. One could work on logical design of circuits or compilers or combinatorics, and the frontiers were not very far out. And there were a host of problems that came up if you did any computer programming, problems would just jump out at you. And so there were a lot of things to work on. Now, some of the areas, now it's a little bit more like the world of mathematics. In pure mathematics, the frontiers are very far out, and there's a high degree of specialization, so that somebody in topology might not have any ability to communicate with somebody in logic or differential equations. That kind of depth is beginning to occur in some areas like cryptography, for example, or quantum computing, where you have to know a lot to contribute. So I would say that the preparation that one needs and the degree of specialization that one needs is much greater now than it was when we were just blazing new trails and encountering lots of things that we could attack.
I'm going to just take a quick look at these questions, see if I missed anything. Well, actually, the last big question I suppose I'll ask is, what do you think is the most interesting question, the most interesting problem, or some of the most interesting problems in your field and that still capture your attention and are worth attention from the young researchers?
Well, P versus NP, but of course everybody wants to solve it. Only one person will, and that might not happen for 50 years or longer. Understanding AI. First of all, I don't believe that we have achieved any degree of what I would call artificial intelligence. The so-called AI systems that we have are focused on particular stated problems rather than requiring a sort of general ability to adapt to the world, which is what you would, and respond cognitively to the world. So I don't think we're anywhere close to having what I would call true artificial intelligence. But there has clearly been very impressive, there have been impressive advances in classification, pattern recognition, some areas of robotics. And there's an absence of modeling in the work that goes on there. What people do is gather a lot of examples of some concept. If you want to build a software system to distinguish cats from dogs, or instances of a concept with instances of its absence, what you do is you build a large training set and you hand it to a very ignorant system, which is sort of generic. It's like an arbitrary interconnection of neurons, and organized in layers, and you give it these examples, and then you juggle the weights of the neurons according to their correlation with the successful solution of those examples, and somehow there emerges a reasonably good recognizer. The results have been shockingly impressive. but they don't yield insight. So yes, you can build something that will recognize Tom Geller's face in photographs, but you won't know, you won't really understand what the basis for it was. Also, there's this kind of instability. So if you change one pixel in his image, he'll suddenly be classified as a cat instead of Tom Geller. So we don't understand these things, and we don't gain insight along with the successful performance. And there isn't a lot of transferability from one task to another. So I think to devise AI systems for classification and pattern recognition that lead us to insight into those problems, rather than just a recognizer, a vastly complicated recognizer that seems to perform well. I think without the insight, we really aren't there. And furthermore, if the application is safety critical, like steering an airplane or driving a car, a system that allegedly has learned to do it, but one that you don't understand, really can't be entirely trusted.
Do you believe that it's possible to instill insight, true insight?
I hope so. I hope so. Another issue that is very interesting is some of the issues of ethics and fairness that arise when computer systems or algorithms are being used to make decisions, to decide whether to give parole to a prisoner or offer a loan to an applicant, or admit somebody to medical school. I guess we don't use algorithms to admit people to medical school yet, but we do automatically make decisions about job assignments and loans and so forth. The question of whether it's done ethically and fairly, what fairness even means. If you look at the methodology that a bank is using to issue loans or deny them, how would you decide whether it was racially biased or whether it tended to make the same decision about individuals with similar records, or whether it was capricious? Questions of or whether we were using our resources ethically. I think that requires a lot of work at the boundary between the social sciences and computer science. So that's another area. Understanding what quantum computers can do will be, there's the potential that quantum computers can be more powerful than so-called classical computers. We know that quantum computers can factor in principle, we don't know how to build them yet, but in principle they can factor integers much more rapidly than classical computers can. What else can they do? Will quantum computing really provide ultimately a great leap? Or perhaps we'll find that the technical details of making them work are too difficult. Data science for the masses, educating people to critically evaluate data, I think that's an important direction. Those are some of the directions.
Quite a few.
Yeah.
Is there anything else that you feel that you'd like to talk about, or that you feel I should have asked?
No, I'd like to sort of close by saying that I think that this symposium is a wonderful event, and it's made wonderful by the youthful spirit of the people who come, and it's just a joy to see all of this diversity, meet people from other parts of the world, places where I didn't even know that science was going on, and they're a pretty upbeat and interesting group. So I've just like to thank the organizers and say that it's been a very valuable experience for me.
I'm sure they'll appreciate it. Thank you so much.
Thank
for
you.
taking the
You're
time.
a very good interviewer.